Okay, we are now recording, I believe. And we are in chapter 2.
Dr. Brady,
Yes,
did you spotlight the video?
yes, thank you. You can't tell it over here, but it says it over here.
Okay.
Yep, thank you. Appreciate that. Okay, so yesterday we talked a little bit about differentiation formulas again. And as I said to you, the reason that I gave you so many different sections all at once was because I want you to play around in each section. I think that that's helpful because if you only do 20 problems in one section, that teaches you about that, but it doesn't teach you how to recognize other things. So that's what I decided to do. Now, overnight, sometime last night, I changed everybody's due date to next week on all of the things, two different things. One, you have a test to take at home that I gave you last night about midnight. I think I sent you an email about that. So you should have had an email telling you have one. You have a retake, it's due Sunday night at midnight. I opened up all of chapter 1 things until Sunday night. So if you want to look at some of the web assigned things or do more or whatever, you can do that too. That's chapter 1. The chapter 2 ones I also moved. Now, you can be upset that some of them are all the same day, but the whole point is they weren't on the same day, but I moved them all just a week. I didn't worry about, should I make one on Wednesday and one on Thursday and so on. I'm hoping you have enough time so it doesn't come down to the night before you got 5 sections to do. I hope so. Anyway, we can move those too. And we talked yesterday about moving everything to December. However, I looked at the web assigned materials. Some people have not looked at all about any section of chapter 2 yet. I mean, haven't even opened it up. Well, that we're not going to tolerate. You guys got to do something. Open it up, do one problem, and then you will not have my wrath. Okay? In other words, I just want to see that you're working. And when I look and see a bunch of no look, it doesn't say that, but it has an N, it means I know you haven't even opened it, because when you open it, that changes it to the classification. If you haven't even opened it, you're not doing homework. And that's a killer, okay? Now, some people are complaining they have too much to do. That's okay, because I'm happy when you do homework. Okay, so we talked about implicit differentiation yesterday. If you have your books, I don't mean right now, but if you have your books, you might see I'm on page 165, how complicated the graphs can be for functions. Much more, I don't know how well you guys can see this from class here, but you get these pictures that look like mosaic patterns, look like things on the floor or something, because they get very complicated. Humans can't do that, basically. It's just too complicated. And we didn't have these kind of pictures in books before computers started graphing them, okay? Because that's what they are good at, producing pictures like that. Some of the first microcomputers really made pictures before they did anything else. Okay, they couldn't add 3 plus 5, but they could show you a nice picture. What I mean by a nice picture, I'm talking about squares, 24 by 40. Okay, but at least you got pictures. Okay, and since then we've much refined that so that you can get very good looking stuff now. The pictures they show you on those pages are certainly not functions of X. These are things that cross the vertical line, crosses it hundreds and thousands of times sometimes. But locally, maybe we can do that. So that's what we were talking about yesterday. There's not much to do about that other than to treat things, assume there's a function, and stick in, I hope that you will stick the f of x in there so that you see it. Get rid of the y numbers. You will find in the end that's easier to understand, even though some of you might feel like I did this in high school and I know how to do it. Okay, then you've got to prove that to me. Okay, I know how to do it that way too. But I don't care what notation you use as long as you understand. But a lot of times people don't understand, use bad notation, and it makes it worse rather than making it better. So in my experience, I suggest you change that to f of x and see what happens. So now, in 2.7, as I said yesterday, it is mainly a set of paragraphs to talk about different areas in the world where we might use derivatives, okay? And not because of our time, and some of you think we're going fast, but actually we are needing to go faster in certain places, hopefully not in understanding. Anyway, if you read some of these, and I'm going to look at a few of them, but I do not want to require you to be experts in biochemistry or something, okay? I'm hoping when you look at stuff, and I'm going to hopefully put this up for myself here so I can read it here just a little bit. Basically, there are some examples that we usually use in a math class that are involving physics, okay? And so for that particular set, that's on page 170, the book has an example, and I'm going to put it on the board here in a minute. The position of a particle is given by a certain equation. Now, the idea here is that we're thinking about straight line movement. The position of the particle is like along a road, okay? We're not trying to make a graph of the movement in terms of like, what's the shape of a road? Is it like the shape of a sine curve? We're not worried about that. We're worried about how far you get away from a certain place and when you're going away from it and when you're coming back to it, okay? So when they say the position of a particle is given by an equation, and they're using S for where you are and T for the time that you are there at that spot. And so we've changed XY to S and T, except T is a domain. In when you do XY, you think of X as first and Y is later in the alphabet, that's second. The X is horizontal and the Y is vertical, okay? If you take S and T, the S is horizontal, the T is horizontal and the S is vertical. But we're not worried about picturing the graph that you get by the equation. What we're thinking about doing is moving along a straight line in time. And the formula tells you where you are. It's not the same as graphing, okay? So when you look at the formula as the T is time, then the first derivative is called velocity. And the second derivative is called acceleration. Okay? Now, the absolute value of the velocity is called the speed. So there are new names we use, but it's not new theory. It's just instead of differentiating with respect to x, you differentiate with respect to t. But if I have t squared instead of x squared, and you differentiate, you'll get 2t instead of 2x. So all the formulas are the same. There's no new derivative properties. It's new interpretation of what you are getting as an answer. And what is velocity? It's how the distance is changing in time. What's acceleration? Is how the velocity is changing in time. Now, when we get into more dimensions, velocity and acceleration will be vector kind of quantities. And vectors have directions. So it turns out that we can use the sign of the derivative if we're moving along a straight line to tell us which way we're moving, okay? So if the distance is growing all the time from where you start, all right? If the distance is growing, then that would make the derivative positive. If you think about the XY axis, if one thing is always getting bigger, it makes the slope positive. Anyway, what we can do is interpret how you're moving along the line based on the sign of the velocity and the sign of the acceleration. We're going to get into that just a little bit more. But it's all interpreting the same stuff you've already learned how to do. So it's not new theory, it's just new interpretations. So the first question for this, and I'll put it up here in a second, it's t cubed minus 6t squared plus 9t. That's the formula. T cubed minus 6, whatever I said. I hope this is what I said. 6t cubed minus 6t squared plus 9t. That's the formula, and we set that equal to s. Now, that is also, if you like, you can call that a function of t instead of a function of x. So what's the derivative? If you use f, the derivative would be 3t squared minus 12t plus 9, which, if I need to use it, I might consider dividing by 3. I don't know if I would or not. It depends on why I'm doing it. But that may or may not be something I would do, but I know I can do it because I see the 3 every place I can factor if I want to. May not be necessary, may not be something I need to do at all, but I don't know. So I think that way. The second derivative, a derivative of the derivative, would be to take this, and now I would want to use this first thing, not the second thing probably. That would be 6t minus 12. Now I can take 6 out if I wanted to. Okay, fine. So all I'm doing right now is using calculus with t instead of x. Okay? But what we do is, instead of f, all right, what sometimes we do is call this s of t. The book doesn't use capital S, but it should. So s of t is little s. I use capital 1 to distinguish the function from the variable. And v of t is the derivative, and a of t is the second derivative. And again, all this is doing is renaming the things. Okay? We use the second derivative v for velocity, and the first derivative for velocity, the second derivative for acceleration, and we steal the first letter of those names, those words, in order to name the functions. Okay. Also, by the way, sometimes when you differentiate with respect to t, people write dots. You'll see a dot instead of a prime, but it's not used in our book, but you may see that elsewhere. Okay, so what's the velocity at time t? That's part A. I just did that. What's the velocity after 2 seconds? You stick 2 into the formula. So I would stick 2 into 3 times t squared minus 4t plus 3, whatever that number is. Not what it means, but that's the answer. After 4 seconds, you stick 4 in there. When is the particle at rest? Well, if you think about movement, it's when the derivative is 0. Okay? Because if it's velocity, it's when the velocity is 0 is when the thing is stopped. So to do this part, you have to solve the equation t squared minus 4t plus 3 to see when it's 0. It's a quadratic equation. You'll have 2 answers. So evidently, in this particular scenario, there are 2 places where you stop. Okay? Now, if we were to graph this function, it would be a parabola. And so the graphing of it has nothing. I'm just going to make up a graph here. It's not necessarily accurate, but I'll just make up something. Now, we can sometimes learn from the graph things about the movement along a curve, along a straight line. Remember, this is not the road. All we're doing is moving along something back and forth, perhaps. Okay? But the value of this, if this is v, if I look at this, the v for certain t's, this is still t now, and this is the v-axis. So now, again, I would prefer if we used a capital V for the name and little v for the value, and a capital A for the name and little a for the value to distinguish between naming the function and naming the variable, but the book doesn't do that. Okay? So sometimes we will write the capital, what I'm using capital here, sometimes we put it in boldface or something, so you can tell it's something besides a variable, it's a function. But boldface is used for vectors and stuff, and so I don't like to do that. Anyway, if I graph this, if I look at the graph, if this were an accurate graph, this is when the velocity is positive, this is when the velocity is negative. What does that mean? Okay, it has to do with which way you're going along the line. You start at a certain place, you go away, that's going to be positive velocity. You come back, it's going to be negative velocity. What is where you stop? That's probably where you're going to change direction, not necessarily. You could pause before you go on. That's going to change the shape of the graph. So we can study graphs to help us understand movement. Okay? But it's harder to think about it because this is not the graph of the original function. This is the graph of the derivative. And there are problems in WebAssign and in the notes here where you have to interpret graphs. We'll talk about that a little bit more later. So the part D, it says, when's the particle moving forward? And so when are you moving in a positive direction? That would be when your direction, when your distance from the starting point is growing. And that has to do with when the velocity is positive and so on. And so what you have to solve now is when's the velocity positive, negative. So you know where you stopped. Now, in our case, I said I may or may not have a reason to do this, but in this particular case, if you factor, you get t minus 1 and t minus 3. And so it looks to me like I drew a relatively accurate graph in a sense, in that I have two places where the velocity goes through the horizontal axis via 0, and that's two places. So what's going to happen in between? Well, you can read off up to 1, the velocity is positive. After 3, the velocity is positive. In between here, it's negative. Okay. And so, you know, there's two things with when you have a graph like this. When it's up here, it's a plus something. When it's down here, it's a minus something. The something it's a plus or minus to is called the speed. Okay. So this says I'm going at some speed. It's a negative number, but the negative has to do with which way you're going, and the amount of it has to do with how fast you're going. Okay. So a minus 10 is going 10 in a certain direction, but it's faster than a minus 3, even though it's a smaller, the number is smaller, but with interpretation is that the speed of minus 10 is 10. The speed of minus 3 is 3. So minus 10 is more speed. Okay? When are you speeding up and when are you slowing down? That's when the acceleration is changing. But you can be accelerating going away from the thing, or you can be accelerating coming back. That's when the velocity and the acceleration have the same sign. So what you need to do to talk about speeding up and slowing down is seeing when the signs here change. In this case, the acceleration is positive if t is bigger than 12, and it's negative if t is less than 12. Okay? And the velocity, we said, changes in 3 different places. So you have to put together these two things. If I, wait a minute. That's 6. When I take out the 6 is 2. I thought 12 was too big. That's just a dumb mistake on my part by not being able to read what I wrote. Okay? So it's when t is 2 that things change. So t is 2 actually turns out to be in the middle here. Now I haven't drawn for you the acceleration graph, but basically if I'm bigger than 2, the acceleration is positive. If I'm bigger than 3, the velocity is positive. So when am I speeding up and going away? When I'm bigger than 3, because bigger than 3 is bigger than 2. So when you're doing both, you're speeding up, all right? When I'm doing both over somewhere else, when t is less than 2, then the acceleration is negative. So when is the velocity negative? Between 1 and 2. So between 1 and 2, the velocity is down here, but the acceleration is negative, and that means I am speeding up, going the other way. Yes? Somebody wants in? Okay, who wants in? Ibrahim wants in. Ibrahim, I'll let you in for $1. I can't say that to him until he's in, so he can say, I'm already in. Okay, thank you. Okay, so everybody kind of gets the gist of this? They'll ask you little questions about the derivative. The calculus part's easy. Trying to figure out what does it mean. Okay, you got to think about it a little bit. Okay? All right, so he spends a couple of pages on that, and that's fine. I don't misunderstand it at all. Okay, so then he tries to show you some graphs as well. We might talk about that later. Example 3, and I'm trying to see where example 2 went. No, example 2 is having to do with a rod. A rod or piece of wire is homogeneous, then its linear density is uniform and is defined to be the mass per unit length and all. So we get into physics, okay? Fine. Suppose, however, that the rod is not homogeneous, that its mass is measured from the left and so on, as a function of how far it is from the end. So what do you get again? You get a function, okay? What's the derivative in this case? It has to do with how the density is changing as you move away from the end, if I just read that fast. He explains it, but again, if you're given a formula, you can just differentiate it. The calculus part is now easy, okay? It's trying to understand the physics, which becomes more of a problem, and the point is, it's not a physics class. So I want you to understand that, but I'm not going to test you over it, okay? Number 3 talks about current, all right? And current, you know, has to do with how electrical things are changing in time. So these are the physics things he gives us. And again, you read them, you say, oh, the change of current in time, that's a certain thing. And if they give you a formula, you can find the derivative. It's easy. Okay, chemistry. He points out here, 2 molecules of hydrogen plus a molecule of oxygen gives you HO. H2O. Now, we used to, when I was in high school, we used to call water HO. Unfortunately, since then, HO, if you used to say somebody is involved with a HO, it's a different thing. And I don't know what that even means because I'm a nice person. But we used to call things HO, and our parents would get upset, but we didn't know about the other meaning, you see. So I'm going to go get some HO, you know, and everybody, all I want to do is get a drink, Father. Don't get excited. Anyway, that's what we used to call it, not knowing what it was we were trying to say. Okay, so sorry that's being recorded. Anyway, we have, I hope I'm forgiven, we can work this into some mathematics because we talk about concentrations of stuff. And again, what Cox is all about is measuring how things are changing. And they can change in time, you can change with heat, you can change with moisture. There's all kinds of different things that can change that may or may not be relevant to time. Okay, but a lot of things in life are relevant to time. And so a lot of things in physics and chemistry are related to time. And so we use T, but he tries to talk about concentrations of things and how they're changing. And he says that chemists are interested in how the rate of reaction of a process. Now, I had a problem given to me once during a test, and to me, it was so funny, I had trouble answering the problem. And that was the following scenario, and it was physics, but it's still chemical anyway. It was a 60-kilogram ball of putty. That was the start. A 60-kilogram ball of putty is traveling through the air and hits somebody, okay? Collides with somebody at a certain speed, okay? And so, I mean, all my concentration about doing math is kind of lost because I'm viewing this thing. And then the next sentence is where I really went nuts. It says, the collision lasted 2 seconds. Okay? And so I got this sort of thing that happened. Anyway, so I really had trouble trying to answer the problem because it just made me laugh thinking about it. Okay? So usually in math, you don't get a chance to laugh, so I guess that was okay. But I thought that was an interesting problem, and it had to do with, of course, the material and so forth. But anyway, what you're interested in chemistry is the instantaneous rate of reaction, they say. Because you can talk about how something reacts in time and how much it changes, and then the question is, if we cut down the time and do it in shorter and shorter times, that's what derivatives do. Okay? And so in chemistry, you have an instantaneous rate of reaction. In thermodynamics, that's can be physics or chemistry. They talk about how something's compressible. You may have heard that water is incompressible. If you jump off a 10-story building into a swimming pool, that happens in movies when the police are after some guy and he jumps out the window and he lands in the pool, that's a big problem actually, for 2 reasons. The fluid is incompressible, so it's like landing on cement. And secondly, the pool is not very deep usually. So 2 things may happen to the person besides what you see on TV, which is a guy splashing around afterwards. Okay. There's another problem when somebody jumps off a building and Superman catches them on the first floor, of what would happen to that body when the person catches you, which is no different than hitting the floor, you see. If you think about it, because if you stop them, you're doing the same. Okay. Anyway, so what Superman should do is go up and fly with them and grab them and then not hit the ground, you see. But I worry about these things. It ruins the movie. Okay? It can't help myself. It ruins the movie. Like somebody who can pass through walls. Why didn't they pass through the floor? I don't know how you ever get to the wall. Because you'd be gone. You'd end up in China or somewhere. And then if you did, of course, you'd come back. So that person is going to be, anyway. I think these things, you see. Okay, so anyway, we have incompressibility. Fluid flow, for example, if you're studying flows of fluids, we make some crazy identifications, like the flow in an artery is like the flow in a sewer, whereas the flow in a capillary is like a flow in a very small space, okay, like something like a faucet. And the idea is whether or not you have to take the wall effect of things passing past the wall as to whether that affects the fluid. Understand? Because if the fluid is changed in terms of its speed by its reaction to the wall, and it's a small circle so that the wall is close to the size of the particles going through the wall, then you have to take that into account. Whereas if it's a sewer, the idea is that most of the stuff is way away from the wall. So it turns out there's two different mathematical models for such thing. Like there's a different model for veins than there is for arteries in math. Same, and it's the same as people use in sanitation, okay? Although the people using it may not know that, but it's two different mathematical models. So you have to decide, like, for example, do you know about high-rise cats?
Isn't the cat where it's like half dead, half alive? Isn't that the cat that's half alive, half dead?
That's Schrodinger's cat.
I
Yeah.
think it-
It's cats that survive when they jump off high buildings, okay? First, I think discovered in Miami, because they have lots of high-rises and lots of old people that have cats. And every once in a while, you let the cat out on the balcony, and after a while, the cat's not on the balcony. And then there's a possible problem. Well, they found the cats were fine, they're just down on the first floor. Anyway, there's a problem in physics with how they do that, because they have to change their thermodynamics, and you're not supposed to be able to change your thermodynamics in a fall. And so cats change how they are so that they survive. Sometimes they have a broken leg or something, but otherwise they're okay. They're called high-rise cats. Okay. Humans, if I ever go off a tall building, I'm going to try to figure out what the cat would do on the way down. Why not? You see, why think about something else? Why not think about how to survive? Okay. Anyway, so once upon a time I studied this idea, because in case it ever happens to me, I'm going to figure out what to do, you know, how to change my thermodynamics, or not thermodynamics, that's a different question. Okay, so anyway, what I'm hoping you guys do is read through here, and it actually gets, when it gets to biology and it gets to flow, laminar flow and stuff like that, he actually starts doing some computations, but that's because he gives you formulas. So I'm hoping you read through those things. There's some economics in here, having to do with cost and margin and that kind of stuff. If you're in a field where you will be learning a lot about some subject like chemistry, I suggest you look at that paragraph real hard and maybe do some problems in the exercises involving that. So speaking of the exercises, what you will see in most cases in the exercises are all sort of word problems, but most of them will give you a formula to derive or to play with. And for example, if I just my eyes fell on problem 18. If a tank holds 5,000 gallons of water, and we're going to talk about tanks in a little bit, because there's some dumb tanks out there, which drains from the bottom of a tank in 40 minutes, then Torricelli's law, see, that's a formula. Torricelli's law gives us the volume of water remaining in the tank after T minutes as, and you get a formula. And it's got some T's in it. Find the rate at which the water is draining. Now, all you got to do is differentiate the function. So this is not a hard word problem, because they're giving you the formula. Okay? And so forth. So, and there's all kinds of, by the way, there's lots of interesting things about water flowing out of a small hole in the bottom, because the dynamics of it is very interesting. But we're not going to get into all that. Okay, that's for other courses to do. I hope you take some of those courses. What I'd like to talk about from now is what's called related rates. Because what I want to do, and that's the next section, by the way, but don't worry about this section. You're not going to be tested over. Just read some of it. Play with it a little bit, okay? But the related rates, you will be expected to know some stuff. But I want to try to show you how to do related rates. So all the calculus is about how things are changing. Could be in time, it could be in weight, it could be all kinds of different reasons to change with respect to, okay? And we're going to talk about certain ones of them. At least I am. Now, the first problem, let me read you the first problem. it says air is being pumped into a spherical balloon so that its volume increases at the rate of 100 centimeters cubed, it's cubic centimeters per second. Now, as soon as you see something / per something, that's a derivative. So when you read a story problem, you've got to interpret the thing. And as soon as you see miles per hour, that's a derivative. Okay? Because it's rate per something. Okay? And this is cubic centimeters per second. So that's going to tell you the variable that's independent is going to be time, and it's seconds. If they give you the time in minutes, you change that to 60 seconds. Okay? If they give you a diameter, but the thing's radius, you need to change that. So you need to think a little bit about what they say. But anyway, and where you put equal signs is usually where the verb is. Okay, anyway. Air is being pumped into a spherical balloon so its volume increases at a certain rate. Fixed rate. How fast is the radius increasing when the diameter is? Now, there's a trick in there. How fast is the radius increasing when the diameter is? You see? You don't want to take the number they give you for the diameter as the radius because that's wrong. So you got to read the problem. Now, big thing in there is the word when. When. Because that's one time. Maybe a couple of times, but it's at a fixed time. So now, what do you have to know to do the problem? It's the volume of a spherical balloon. I need to know the definition for the volume of a sphere. Now, in this case, the book doesn't tell us in this problem. So, fortunately, in the back of the book, there's a list of things like this. But somehow or other, you're supposed to know what the volume of a sphere is. Now, what I learned once upon a time was this formula. And that's why I never got out of math in high school. Because it's actually cubed, right? I'm only doing that to see if you guys kind of remember it. 4/3 pi r cubed, is that right? Mm-hmm. You agree? That's it. Okay. Now, if you didn't know it, look it up. So one of the problems here is the author may be assuming you know something you don't know. So ask, what's the volume of I don't know what, a hyperbolic paraboloid? I never heard of that before. So ask. If they give you a problem like that, don't say, I can't do this problem because I've never learned. You're not supposed to learn them all. Now, the ones the author thinks you don't know, they will give you formulas for. But this is a formula I learned once upon a time. Okay? I don't want to use that formula because I don't like it. No, I don't mean I don't like it because it's ugly or something. I mean, what we're talking about here are things changing in time. And the radius is changing in time, and the volume is changing in time. So I highly recommend that you make these things functions of time. The things that are functions of time. 4/3 is not a function of time. Pi is not a function of time. Okay? But the radius is and the volume is. So this is what you should do, in my opinion. The book doesn't like to use functions, they like to use variables. I highly recommend you use functions, and I'm going to show you why. It will keep you out of trouble, but I'll show you why. So what does the information from the book tell us? It tells us that it says the volume, air is being pumped into the balloon, so its volume increases at a rate of. So V prime of t is 100. Now, they give us the stuff here, centimeter per cube second, that's important, but for the math, it's not important. It's only important to get the numbers right to start with. And is it plus or minus? There's a word it is increasing at, that means you put a plus on here. If they said the volume was decreasing, like your tire just blew, the volume is decreasing in time, okay, you put a minus there, okay? So it might be more than just a number. It might also involve not the original formula, but the derivative can be negative, depending on the circumstances, okay? So that's, now, something I forgot. That is, for all time. In other words, this is a constant change. So you ought to say, it's not changing in time. He says it's increasing at a rate of. It doesn't matter what time it is. Now, of course, after a little while, there's going to be an explosion because the balloon can't fill the earth, you know. So this only works in a certain time frame, but what we basically do is ignore the idea that it's you know, like I'm not worried in 12 minutes what happened. No, just worry about what's happening while it's going on. That's the idea. So I don't know the limits of time, but probably I might think it's greater than or equal to 0 because what's negative time and get me all philosophical. How did Julius Caesar know that he was born in 44 AD? He developed a calendar. How does somebody, when somebody asks somebody their birthday, 100 BC, how do they know to say it's 100 BC? You know, you're supposed to know the year you were born. I was born in 101 BC. You think that's what they knew at the time?
No. BC before Christ.
Well, I know, but what were they doing in BC? They didn't know it, but they were counting down. Because how do we refer to them? Time's going down. If you're born in 20 BC, you're younger than the guy that's born in 40 BC. Right? So while they didn't know it, they're counting down. Time is going different. As soon as you get past something, then you get into time's going up. Maybe you never thought about that.
But isn't that purely retrospective? Because at the time they weren't counting down to like the birth of Christ, because Christ wasn't born yet. They would be counting up from their system of years.
Yeah.
So,
But the people then, what'd they say? Who knows?
I don't know how the Romans count the time.
Yeah. Anyway, maybe they didn't worry about it.
They probably.
You know, maybe I know I said you have to be 21 years old to have a drink, and they say I was born in 46. Anyway, I'm sorry. I worry about these things. Do we have this? So we had the Julian calendar. What do we have today in America? The Georgian calendar. You know that? Anyway, just to waste some moments here, which I shouldn't do, but I shouldn't say it while I'm being recorded, but I think it's like 1535 or 1555 or something. We changed the calendar. Okay? For example, when George Washington was born, he celebrated his birthday at a certain month of the year, certain date. But when he was growing up, he celebrated his birthday at a different date. Why would he do that?
Because we fixed the calendar, because the old Julian calendar had too many, or basically we weren't having enough week days. We were drifting off of when each season was.
Okay, so I don't know if everybody's understanding him through the mask, but basically the new calendar in the 16th century, George Washington was the 18th century, but in the 16th century, somebody changed the calendar because they realized that since the Julian calendar was adapted, they had there's not really 365 days in a year, you know. It's a little bit off. That's why we have leap year every once in a while to correct. Well, they found out they were about 2 weeks off in 1555, or that's probably not the right date, but roughly. Who was the guy that did it? The Pope. It's the Pope's name. The Pope changed the dates for people who are Roman Catholic, which includes some countries in Europe. Why was George Washington changing in the 18th century?
Because it takes time for all the non-Catholications to change.
Well, it didn't just take time. The point was that Britain didn't change because they weren't Catholic after Henry VIII. And they said, well, the Catholics may want me to change, but I'm not going to change because I'm British. So those parts of the world that were British didn't change. And America was British. It didn't change. And so George Washington didn't change until after the revolution. And once we became a country, we changed the date because we separated from England. And scientifically, you need to change the date. Now, when do you think other people changed the date? Like, when did the Russians change the date?
In the 1900s.
In 1919, because of the Russian Revolution. When did the Chinese change the date? The mainland Chinese?
In 1930s.
1949. When the communists came in, they changed the date. So unknown to me, for hundreds of years, people in different parts of the world had different dates. I never knew that until recently. I find that interesting. Do you find that interesting? I don't know.
Yeah,
So
right.
it's important sometimes to delineate where you are and what time it is and all that kind of stuff, because people might disagree and you need to have a fixed thing. You need to be clear about it. So in this particular case, the volume's not changing. I'll get back to what I'm supposed to be doing. Okay? Volume's not changing. Oh boy. The time has changed since I started talking though. Okay? Amazing. Okay. Now, but I got to finish this because you never want to just leave it out in the middle. So how fast is the radius of the balloon increasing? When? Now, the when is very important. So let T naught, this is what I want you to do. Let T naught be the time when. That's very important. When what? When the radius is, when the diameter is 50. So when D is 50. Now, it's, I have to worry about it's 50 centimeters and so on. That's okay in this case because the other one's centimeters. Anyway, when D is 50, that means when R is 25. Now, it's not R is 25. It's when R of T naught is 25. Because what is R of T? R is what's happening at a time T. So what's R of T naught? It's what's happening at the when time. So I want you to name the when time. Because what are we supposed to find out? We're supposed to find B prime, we're trying to go too fast here. How fast is the radius increasing? So what we want to find out here is R prime of T naught. Not just R prime, just like R prime or dr dt. We want to find R prime of T naught. And so what you do is you differentiate here. I know we're out of time here shortly. When I differentiate, this is just good old differentiation. You're going to get 4 pi R of T squared times R prime of T. And again, when you differentiate the formula, you get something for all T. That's what's going on all the time. What are we interested in? One time. So what you do now is the V prime is all the time, so I can replace the V prime of T with 100. And so what I get is 100 over 4 pi R of T squared R prime of T. And that's true all the time. It's important to know when and stuff. So this formula is always true. Now, we only want to know it at one time. So we take this formula and stick in T naught. So because of my time and the space, I'm just going to put T naught here, but you wouldn't do that first. Okay? So I'm doing this T naught. What do I know about T naught? R of T naught is 25. I've got 100, 4 pi, 25 squared, 625. This what's left over, R prime of T naught. What am I trying to find? I'm trying to find R prime of T naught. So all I got to do is divide by 625, which comes out 1 over 25 pi. But if you say it right, it makes it easy. This is what we're looking for right here. If you use the correct notation, you'll see what it is you're looking for. If you don't use good notation, you'll be like, well, what do I do when I, believe me. So I highly recommend you guys when they say the word when, is denote it by a certain time, because that's when everything's going to happen that they're going to ask you about. Okay? Now, there are 5 examples in section 8. They are different. Every one of them is different. They're very good examples. I recommend, we're going to do them in class, but I recommend you look at them overnight. And one comment, I made a comment earlier about a water tank, and I want, example 3 is a water tank that has the shape of an inverted circular cone. Now, think about a water tank in a city that is shaped as an inverted circular cone, full of water, and is all resting on one point. That's the dumbest city I've ever heard of. How are you going to get this water tank to stay there in Kansas? Think about this huge water tank with a shaped as a cone. Anyway, you'd think it'd be an inverted cone, yeah? But not this one. This is a dumb question. You understand? You'd never have I wouldn't anyway. And by the way, cones have 2 naps. Cones are there's you know, a cone, it's got a top, it's also got the bottom. It's what we used to call, when I was a kid, a German yo-yo. Anyway, it has a cone shape this way and a cone shape down that way. So when I go in an ice cream store, I ask for the other half. Now, if they actually give you a real cone of ice cream, you have to really eat it fast. But usually they just toss me out of the store. And so, okay, I got to